That's what I'm saying. Remember how we were all thinking which one is the best way to measure?
Yeah.
And now thinking of it afterwards, like, it's proper now. All these things. So basically, the only way to measure how good your
Just keep checking.
Yeah. Then if it's like 70, you can go back.
Keep checking.
Yeah, you just work at, as long as
You consider the other one. No. You want the other one? Yeah.
What else? What is other ones that you consider?
So if now
share that on
you're gonna go back to a confusion and see which one, like the misclassifications and that, and check your data, like the main domain. Yeah.
But your point, what are you gonna do? What are you gonna want to do?
Hey, Mara, when you have to.
You should. But you're really. Yeah, no, that's the first one. So now that's the second one. And just comment and say something. The second.
What's left in this? I'm sure, eh? This is
Subona abantu bethu asijayele. Sifana nawe. Wena nyamazi bakutshela ukuthi Friday disappear. You don't even waste time. For sure namanje umele half past 3. Konje nina nitshayisa early ne? Yeah.
really?
Yeah. So what's the plan for today? So you're going home?
Oh yeah, guys. Tell the MDS
Guys, 5 minutes, it's done.
Yeah. Are you also coming? So I'm not coming. I'm
she's not coming.
I'm kidding. I'm kidding, bro.
Okay.
When? What time?
Start like at around 6.
Okay.
So should we bring
So
our
let's ask group A. What was the question? That's the question. For this group. What was the question? Oh yeah, which case is better? No, actually I forgot. I wanted to get to remind me. Which case is better? So I'm sick, but I'm not sick. Okay? Yeah. So you're gonna give me medication. I'm gonna start taking medication, right? Because I'm sick. You're gonna give me prescription. Then I'm gonna. I'm not saying you're wrong, but I'm just trying to put the perspective. Which one is worse? We're trying to balance it. Okay. Okay, that's interesting. Anyone from this group, or should we skip? So they're saying the first case is better, which I don't know which case is which. Which is you sick? Okay, so you're not sick, and then you diagnose as sick. So the algorithm said you are sick, right? Where else you are not? Okay, cool. That's interesting. What do you guys think here? Same thing. Why? No, why? No, I didn't hear any reason. Maybe you can repeat it.
it's better for you to get told that you're sick so that you start taking medication. And then you find out that you're not, rather than you not taking medicine at all and then finding out that like you have 3 days to live and now you can't even
Now-
see your doctor. You see, if you get told
Now, what if the medication that you give me makes me sick?
then you'll see your doctor and still be fine.
Now, in the other case, I'll still sue the doctor.
But you'll see your doctor with 3 days to live, so you won't enjoy the money.
Okay. They've got interesting. We're gonna go. Hello. We'll go to that group. Interesting conversation. This guy says I'll have like 3 days to sue my doctor and none of that. Let's hear. Now, remember, let's say this was images, right? Image classification of cancerous cells, which Jonathan is doing is cancer. Like, let's say it was images. Right now we're using CSVs, right? So at this stage, I'm already being diagnosed, and there's this thing that takes pictures of stuff, whatever, and being fed to the algorithm, right? And the doctor is relying on that. So the doctor is already relying on this. It's not that there's going to be a further diagnosis. It's like the outcome. So the surgeon is relying on this. Let's say this was applied, of course, this algorithm was used in all the hospitals in South Africa, and it was designed by this group here. Right? It's in South Africa, you try to get a second opinion, same results. No, it's already deployed. We've already changed the parameter, we already tuned.
Changing the test.
Oh. Okay. Interesting. They've got a very interesting answer. This guy here, then we're going to ask people this side, yeah. It depends, yeah? Yeah. Yeah, so you die. But remember, this was an algorithm which was built by this group. So they're engineers from UCT, from UJ, yeah, for sure. I'm from UJ, so hey, you like coding? Results, yeah. Publish this thing and okay, I like your answer. It's quite very interesting. Let's ask people this side. Okay, let's ask this side. Which case is better? I can't see it.
Hey.
Cecil. Yeah, already. Answer. Okay. Why? So, okay, cool. Anyone wants to say something? Anyone wants to say something different? Okay, cool. I think that's quite very important. We can clap hands for everyone. That was a good answer. The idea here is to remember you don't want to. Okay, guys, we continue now. Remember, you don't want to be that data scientist who just builds good products and right? Because at the end of the day, there's people's lives at the end of these algorithms, right? There's people who you might ruin their career, There's people that you might just kill. There's people on either cases you give me misdiagnose or misclassification. I might get sick and not decide next year, and you understand. So the idea is that remember that you guys are building algorithms that are gonna go out there and people are gonna use them, right? I was telling these guys there at by the kitchen there that what's his name? Forgot. He's from. You can Google his story. He's from America. So what happened is a black guy who one day he was telling his story there in Black in AI there, where we were attending the NIPS. He could not. He's from America, so he could not come to Canada because of some scientist who built a risk analysis algorithm. Like she was explaining, whether you know or what, so but it depends, right? Where they take certain features and it will either say you're low risk or high risk or whatever, right? Same as the credit scoring, right? You want to go apply for a loan or something like that. But now this one is different because it was taking your information and either the algorithm was saying whether you're high risk or not. So this guy was, one day as he was relating the story, he had to Skype. He could not come to the conference because he has a criminal record, which he did nothing, right? So he was saying one day at night he was chilling with his, I think his cousin, and he decided to go buy weed, right? And he was like, okay, let me go outside and go buy weed. And before he could even get to the store, a police car came. Yo, dude, we need to investigate and stuff and things like that. And he ignored them, and as he was relating the story, he went back and he eventually got arrested. And before getting arrested, they had to run a risk analysis, you know, get his name, his age, where he comes from. This is an algorithm, right? These are the features that you put there and you click predict. This algorithm is going to say high risk, right? They got his stuff, and funny enough, the algorithm was like, this person is high risk. Remember, this person did not do anything. He got stopped, stayed in jail for 2 years, right? Because of this group here. They built an algorithm, and they said, yeah, it's accurate enough, and therefore go boom, right? And it happened twice. So after 2 years when he got arrested, he got out, they caught him. They did not change the model of the algorithm again, right? They did not do any hyperparameter tuning. Put in his data, bam, high risk, he went to jail again. Now it's even worse because he has a what? A criminal record, right? So higher risk now. So, and he did nothing, and he's an honest human being. And these are the algorithms that you guys built. These are the things that you, I'm talking about a real story about a person. I'm talking about a real story, and no visa. It's very difficult to find a job, and the idea why you need to sort of like dive deep into your algorithm, even though in this 12 weeks you might not do that. You need to get an intuition of what you're exactly doing and getting a feeling. It's not about getting a high accuracy and say, yeah. You need to justify each parameter and why you chose that, and try and minimize biasness. There's other examples where other companies misclassify it, but in this particular case, you would see that there's a higher misclassification there, right? Another way of doing a classification. Remember, we're still doing supervised, and we left like an hour to finish our school, so I'm gonna rush through, but we're almost done. So in like 30 minutes, we should be done. So what we spoke about, it was a false positive, but there's a rate, and there's a true positive rate. So in this particular case, I want to see how my algorithm, what is the false positive rate, and what is the true positive rate. And the rock curve is a score where AUC is called the area under the curve. I'll just show you now how it looks like. Don't worry about the code. I'll just send it to you. But it's just the same thing that what Vaughn was doing. Put logistic regression, X train, Y train, get the probability of the your X test, and your false positive rate, true positive rate, threshold, and you feed this ROC curve. So you import sklearn.matrix ROC curve, and you feed in this, and you plot this. Now, what this means is that the more this red line here is closer, approaching to 1, the more we accommodating more people. So that's what we want to do, right? So in this particular case of ours, the more this red, if it can move up a bit, we would have accumulated more people, right? And it's a good metric to see whether your algorithm is performing good or not. And yeah, so you can see in the algorithm, we are accommodating most of the people because the area under the curve here, it's quite large. So the larger the area, the better. The smaller, but the accuracy could still be high, right? Because remember, your accuracy still looks at your false positive, including your, it looks at everything, right? Your true positive and your false positive. So don't just use that and say, yeah, and stuff. Because there might be a huge number of people that are not represented. The other way of finding parameters, you can do a grid search. So what you do, you can define a variable called grid, the number of neighbors. So we're trying, remember the K that we found before, which was 2, and we realized that no, it was overfitting because K was less. Why? Because in literature it says that, right? Now let's do a grid search. Let's just search and see what's going to happen in our data using our K and N. Still putting the same X and Y, but we want to tune in our parameters. We just say K and N this using the grid search. Get the best parameters. Just say dot best params, and it will tell you that it's 6 and the score of it is 0.75. So now, remember, ask a question: how do we know whether we're overfitting or not? If C is high, we overfit. If C is low, we underfit. There we have it. Let's see. There it's our CV, cross validation, and our score. If C is high, we overfitting and CV. CV. CNN CV, that's the score, the best score. We can compare this with what we had before. This one before, which, no, this was for linear regression. We can compare that with what we had before, with K equals to 2, the number of neighbors. We got something like that. And this outputs on N is 6. What is it? So grade, which is case from 1 to 50, excludes. So it's almost similar to what we wrote before. But here, the only difference, we did a grid search. Okay, I don't know why it's saying 4 now. Okay, which one is this? Okay, let me see which one is this. Oh yeah, so these are our regularization parameter, and the penalty, if you go on the documentation, you will see that there's L1 and L2, right? And the hyperparameter grid, or what we were trying to tune, our K, it has, depends on L1 and L2. Doing a grid search, but now we base that, we change our random state, which was different from here. which was 42. So I'm surprised why none of you did not ask why we used 42 here and why we use this one, and what will be the difference. Did anyone get the question? Did you guys get the question? I'm saying here, we're still using a grid search for logistic regression. Our random states here, I chose 12 and I think it's 42 here. If you're interested why most of the people choose 42, I'll put a link why most of the people choose 42 as their random state rather than choosing one. If you've seen most of the examples online, people are using 42. There's a quite very interesting paper, and there's quite interesting arguments why people choose 42. I'll just put that on Slack. But most people, they go with a random state of 42. And like we said, we spoke about, is that this has to do with our sampling. And somehow when it's at 42, it performs better. Okay, here. Okay, yeah, here's a quite very interesting part. So in real life, we might not get the data that we got, right? The data that we got was nice, am I right? It was really nice with labels there and stuff. So how do you then do pre-processing of data? I'm sure that label did cover this. I'm right. Getting dummies. Like if you look at what we've been applying so far, we just applied a KNN and logistic regression. If you go to other algorithms like a support vector classifier, you cannot feed that class as abnormal or normal, right? So you need to pre-process your data. So some of you might want to use, you might not want to use KNN. Let's say you might want to start tuning or studying with support vector classifier, and that it won't take data which has a class. Where is this? You cannot input this into the algorithm itself. So you need to find a way to pre-process that. And this example, this is was quite easy because we were having two variables, which is whether a person is normal or not normal. And the best way to do is to say get dummies, and get dummies will just give you extend that column. Let's go to class here. Sorry, excuse me. It will say class abnormal, and then we put a 1, and it's 0 on the other class normal, and it will switch vice versa. Then from this you can drop one column because it just represents your binary data, where 1 is abnormal and 0, it will put 1 on the other side if that particular column is normal. So you can drop one of these to represent that. And the reason why you want to do that is that this, you can feed it into your SVC or support vector. Okay, I know Lebu did cover that. And you can also if you go to the documentation, sorry, I'm rushing. But if you look into the documentation of your sklearn, if you go to sklearn.svm and import SVC, you will see that it has some parameters. It has gamma, it has some funny other things that you don't understand. Still the same thing, but the only difference is that we're doing a grid search, which parameters that we can use. Gamma between 0.1 and 0.011 and Vaughan did cover this in her theory, I'm sure. And for an exercise, just fit this and predict and see if you can beat this accuracy without doing a grid search. And you'll see a value why you have to do this. And so the tuned model parameters is that you'll see in your support vector classifier, the best one should be 100. Your gamma is 0.01. Let me just check it. Internet is quite slow here. Okay, cool. But it's fine. I'll wait for it to continue. But you will see that there's parameters within that. And this is how you do it. So just to catch up before we go do an unsupervised learning, we'll be done probably in like 15 minutes because this section is small. I'm just going to cover k-means and PCA and getting the variances of the PCAs. So, to recap, what we have done is we did a supervised learning and we did KNN, and we just started by just putting values and see what we got, and the accuracy that we got for the first time was good. For DSIDE, yeah, you can take that and just go do it for the dashboard. But the second thing what we've learned again is how to tune the parameters for KNN and how to tune parameters for a logistic regression. The reason why logistic regression in this case would apply is that we've got binary data. It's either you 0 or 1, normal or abnormal. Depending on your cases and your data set, you will have to choose the correct algorithm for your application. This is not one hammer that you can solve all the problems. Some other things, they require you to explore your data more and change stuff. And then what we've also learned is to pre-process the data for other supervised learning classification algorithms like a support vector classifier. For that, you need to have, I can say, numbers or numeric to fit it so that it can work. Because if you don't have that, it will just give you an error. So that's why you have to change that column to get dummies. If you had more than 3, 4, or 5, or 6 classes, maybe you wanted, let's say it was more general with different types of classes. We could use get dummies, but now get dummies give me 1 and 0, so it's not advisable. So there's other things where you can use a hot encoder and try to encode what each class in your data represent. Simple example, maybe would be, for example, let's say I've got 3 classes, which to say if n is 1, abnormal is 2, and whatever is 3. But doing that has repercussions, so you need to be careful how you do that as well. And that's when you're preparing it for other algorithms like SVC. And we learned how to do a grid search, just like applying the parameters that we want, and it will choose the best one for us. I would love to see this in your projects, to say we got to this stage because of 1, 2, 3, and 4, not just because he accidentally pressed 7 and it worked. Now, let's say in the very same data set, you didn't have the class. Right? So we just got this data set. This doctor was just, collecting data of patients, but did not do the diagnosis, whether to say whether they're abnormal or not. They were just recording. Right? And suddenly they come to you like, bah, I want to know who's abnormal and who's abnormal. And that presents a different problem, because you don't know who's who, right? So that presents an unsupervised learning problem, and that was covered in theory, and I know Linda covered this. In our case, if you load this data does not have the column class. As an exercise, this is what you could do. When you say k means dot n and you get the labels, right? It will give you the labels based on, okay, we'll get there. Let me just continue about this. But this data here, you'll see it does not have the columns class. It's like just data that just exists. But we know that there's people who are normal and abnormal, but we don't know who's who. So the number of clusters that we can put is 2. In your case, you could put, I don't know, depending on how many clusters you want, maybe 5. Those who are doing transport, car, what, bus, train, you'll put those different types of number of clusters and stuff. Maybe trains will fall in the same cluster. But the third part is that the algorithm won't tell you that this is a train or this is a bus. Right, so you can see that there's some 2 stuff here, but we don't know which one is which. But we can just get the labels quickly. There versus 72 and 0. But we don't know which one is which. Right. Which one is normal and which one is abnormal? What we can do is to apply a cross tab so that it can give us the labels. So 0 being abnormal, which were 138, and also 0, which were in this, which were normal, which was 100. So there's a problem. The question is that we know how many classes the data includes, right? Which is cool. But the number of classes are known, right? So you can do a hyperparameter KNN for this. As an exercise, there's something which is called an inertia, and you can Google that and check how it does that. But for our exercise, we already know that we're looking for 2 stuff. Standardizing the data. Let's just do this. I know Linda covered this. Who's seeing this for the first time? Who can explain what this dendrogram or what this thing means. Let's give it a shot. This gentleman. You can see there's two separations there, right? But you can see there's greens and there's that, and they all connect to that. Now let's go back to what Gary was talking about yesterday. Almost done, you see, yeah. So my energy levels, let me get up. So one important thing that people don't get is what they assume is that when you do your principal component analysis, there's something which is called, okay, maybe I should ask this question. What's the difference between feature extraction and feature selection? We need to get that straight because they do different things. Feature extraction and selection. The other one I'm extracting, the other one I'm selecting. Cecil. Who's Cecil? Cecil. Eh? Cecil. Which means he's not concentrating. He knows. Extraction, selection. I can't see from that side, sorry. Just that I'm sitting like this, like what? Oh, I was asking the difference between extraction and selection. Example. Okay, anyone? Difference between extraction and selection. Okay. This which side? That. Oh. Extraction, selection. Difference between feature extraction and selection. Sorry. Okay.
Guys, we spoke about feature extraction and feature selection on Monday. Gary spoke about it when he was doing PCA. At least by now, someone should have
an idea what
an idea of what that is.
And we did feature selection here. It's just that you guys do not know. Maybe you knew. You knew. I know this idea. Yes. This guy said it better. So he's saying, so in selection, so remember when I was doing linear regression, I just went there and looked at my features, my X, and I was like, hey, let me just choose this and this because they have a linear relationship. That was a selection. It was a selection within the feature set that I had. And in the extraction, like he said, is that based on the features that I have, I can sort of create new features without losing the information. And the example one example, Gary did LDA and principal component analysis. And because of these new features, that does not mean that there's information loss. There's no information that is lost, right? So taking something from a 6D space and, I don't know, doing whatever you did not lose information. It's like you reduce it, dimension reduction technique. So, like he was explaining, because of its extraction problem, you won't know what is what, because it's not a situation whereby we went and say, no, this variable contributes 10%, this contributes 20% and stuff and things like that. But we can get that from the variance to see which one have the highest variance. And so how you do it, all that mathematics can be done in 3 steps. You import PCA, and you fit your data, and you get the components. We get our components. Now, Gary spoke about a variance. We want a feature, right? Sorry. Oh yeah. We want a feature, but now this feature, we don't know what feature it was, because remember it's an extraction mechanism, right? But the only best way to see how it contributes to the overall features, we can get their variances. Sorry guys, excuse me. What you can do is that all our features, our PCA feature, you can see that 0 has the highest variance compared to 5. And at this particular stage onwards, you can fit this into your model. And the other thing that you can do is that you can go back and get the labels for it. But for PCA, you cannot get the exact features, what feature is what. You can get the variance of each. And you can see which one are more significant than the other. So this means that we cannot exclude these ones. This one is not significant when I want to tell whether a person is normal or abnormal. For example, if I want to know whether you have a cancer, but you gave me the color of your shirt, does not have a significant. But we might find it interesting that the color of your shirt has stuff and things like that. That is correlated. Yeah, that's it. And we can apply it like this to see how it scatters across, and you can see the most abnormal people, they lie around this, and most of the other ones, they're around this particular piece. And this looks something similar to what we've seen somewhere here. And maybe are those features that we can, where is that graph? Something that looks almost similar. I'm not saying it's this, but there's something that looks almost to that. Something of this nature. And that's the conclusion. You can go get the data set and follow this. There's more other stuff. And we have reached the end of the tutorial. And if there are any other questions, okay, cool. So in my case, I've got the number of components here. I think I wrote them somewhere. So in my case, it will depend on the, wait, hold on. I think I wrote them down. I'll tell you now. In my case, it will depend on how many outputs am I trying to get. And in my particular case, I only have two components. They should be arranged. Yes, there it is. Yeah, sorry. It doesn't really matter. Let's try to change this. Right, because I've already told this that there's only two outputs that I wanna get, which is what, normal or abnormal. So the threshold will depend on the number of them. So if I run this, let's see. Still no change. Right. But let's put one won't work. I think so. Yeah. Why? So, but my threshold depends on the number of components that I've defined, which was 2, right? And I cannot put something which is above or higher than that. So, in your case, it will depend depending on the number of okay, I have to put 2 here at least. It's what? 0. That's my 0. You say we're choosing 0 and 1. Yeah. So we want to choose something between 0 or PCA features that we want to choose based on the variance. Remember, the higher the variance, it tells me it's most significant. So I want to choose 0, 1, 2, 3, maybe 4, and 5. That is why if I change this much, it does not really affect that much, right? There's no, I don't know how can I explain it. There's no much difference, even though computationally it could be different. I'm not sure if I answered the question. I don't know, but I can only put higher than that. I think this, but still doesn't change. This won't work. This I can put that. Yeah. Okay, yeah, maybe that should be a homework question. Why, based on the number of components that I've chosen, does not really affect the output? That's a homework question. Any other question? Okay. So let's picture this like this, right? So I've got in your mind, can you think how an 8-dimensional object look like, or 4th? Maybe 3rd, yes, you can see, right? But you can transform that into a 2D, right? But you doing that does not mean that it's not the representation of the higher dimension, right? All you've done, you've just reduced the dimension. That's what you've done. But that does not mean you've changed the original, how the original data set looks like. It's like trying to plot, I don't know if you can do it here. I'm not sure, maybe it's possible these days. Trying to plot a 5D graph here. I don't know, a 6 or 8D. I'm not sure how it would look like. You understand? So, but now, if it's on the higher dimension, we would want to like reduce it and see how it looks like. For example, if you look at something in a 3D space, it might completely look different when it's in a 2D. You might think something is linear, whereas it's not, right? Because the way you represented it. But in terms of PCA, we did not lose any information. We just reduced the dimension. It's not that we took, that's what the reason why I asked that, it's not that we took a value which was there and we placed it somewhere so that it can fit our code. No, we did not do that. It's just we reduced its dimension, right? And that's all we did. But in terms of, did we alter the original data set? No. It's like, that's why I made this example of taking a 3D, showing it into a 2D, and then if you visualize that, we can only visualize up until 3D, right? Am I right? Maybe there's other ones that I'm not sure. We can visualize up until 3, no? Yeah, so we cannot, so the best way to do that is just to reduce the dimension, but not losing the original information that we had. I'm not sure if that, but to answer your question, we do not lose anything. Reconstruct it. Okay. Go back. Okay. Yeah. Yeah, you're right. I totally agree with you. It has, but you cannot say it's completely different, right? Yeah, it's you close, because remember here you're doing some maths and multiplications and dividing and stuff, some complex maths and linear algebra. You're right. Going back, we might not get exactly what we got, but it's because of the mathematics and the computation. We are just close to that, but in terms of the error, we are not that far from the original data. So yes, you are right in that particular case. Reconstructing back, we might not get the exact point, but we are close to it, which is almost the same point. I wouldn't say lost. Okay, where's Albert? Who did information theory here? Who did information theory? Maybe might explain better.
Yeah.
Those.
Okay, so first, why would you want to reconstruct your original data if you already have your original data in the first place? Right? Maybe you just want to do that because you want to check if you can reverse map, what you've transformed the data into. But yeah, that's maybe for validation. Right? In any case, I'm going to use Percy's example of having a 3D object reduced into one dimension. Right? Now, that one dimension isn't going to, if you take that one dimension and give it to somebody else, it's not going to map back to 3 dimensions. Right? Why? Because you're looking at a data from a certain perspective, or you're looking at your object from a certain perspective. And that perspective might have certain features that have certain behavior, and that's what you actually care about. Right? In terms of information loss, in information theory, what happens is as soon as you apply a certain transformation to a data set, there's always a certain distribution that will change. Right? As to whether you can reconstruct the exact items, that's a different question altogether. But the statistical properties that you would have, mapped back to, they still remain the same. So variance is one of them, right? But you're not going to get the exact same item, especially for huge data sets. Having said that, the whole point of transforming data or obtaining a model is so that you get an inherent behavior of what's in your data set. Like you want an inherent thing or a pattern. And statistical properties always maintain an inherent pattern or features that exist in your data set. So what I'm saying is it doesn't really matter unless if you want to do validation, right? But for validation, what you use is not the actual observations themselves. What you use are what? Distributional properties, statistical properties. And if those remain the same, then it means you still have the same behavior. So that's fine.
I think the question maybe should be, what if I had my original data set? This is a debate for another day, right? Let's say I've got, maybe the question should be, I've got this output of a PCA, and I'm trying to look at the information loss, right? And maybe that should be the question, the information loss, and how that might be helpful in this particular case. Maybe you might use that to predict some of the missing information in the original data set, right? Not in the original data set, you might be able to predict some missing information. I don't know if that makes sense. Maybe that should be the question. How, given the PCA, how do I map and get the information loss? Hey guys, I've been talking. I think any other questions? If there are any other questions, you guys can. I will send this on Slack. Which can, but any other questions? Logistic questions. I'm not sure. From now onwards, what's going to happen and.
Okay.
Done.
Cool, guys. Let's clap hands for Percy. Awesome.